Module 4, Lecture A, using model.fit. By the end of this lecture, you will be able to configure model.fit with appropriate batch sizes, epochs, and validation strategies for a given dataset. Use Keras callbacks to monitor training, implement early stopping, and save model checkpoints. And interpret training and validation curves to diagnose underfitting and overfitting. Configuring model fit, batch size, and epochs. When setting up a training run, choosing batch size and number of epochs is critical. Batch size controls how many samples are processed before updating the model. Smaller batches give more frequent but noisier updates, while larger batches give smoother updates but require more memory and may generalize less well. The number of epochs controls how long the model trains. Too few can cause underfitting, and too many can cause overfitting, where the model memorizes the data instead of generalizing. Effective training requires balancing these choices to get good performance without instability or overfitting. When choosing a batch size, you need to balance your hardware's memory limits with the statistical needs of training. Memory-heavy tasks, such as medical imaging, often require smaller batches, which introduce more noise but can still train models effectively. Simpler datasets can use larger batches to speed up training and better utilize modern hardware. Overall, batch size is not just a technical setting. It directly affects learning behavior and should be tuned for both performance and generalization. When choosing how many epochs to train a model, consider how complex the task is and rely on validation metrics for guidance. Simple problems may need only a few epochs, while more complex ones can require many more. Because you do not know the ideal number in advance, start with a reasonable upper limit and watch how validation loss and accuracy change during training. Stop when these metrics stop improving, and use that information to adjust the number of epochs in future runs to balance learning quality with computational cost. Python code, batch size and epochs. This script demonstrates how batch size and number of training epochs affect a model by using a very small subset of the MNIST dataset. Because the dataset is tiny, training runs quickly and the results appear almost immediately. This setup keeps the overall process fast and the output concise, making it easier to focus on the impact of these training parameters. The line that begins with an exclamation mark is a command to install TensorFlow version 2.20.0, ensuring the code uses the correct library version for compatibility and reproducibility. Using a specific version helps avoid issues that can arise when different environments have different library versions. In this case, the line is commented out, which suggests that TensorFlow may already be installed, or that running this installation step is optional in the current environment. We start by importing the operating system library so our program can interact with the system, for example, to work with files or environment settings. We also import the random library, which lets us generate random numbers and make random choices, often used for tasks like setting seeds for reproducible results. Finally, we bring in the numerical computing library, NumPy, which is essential for efficient array handling and fast mathematical operations in Python. We start by importing TensorFlow, a library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. We then import the layers component from Keras so we can define different parts of the network, such as convolutional, pooling, and dense layers. Together, these imports provide the essential tools needed to construct and train our neural network model efficiently. We set a seed value, such as 42, so that all random operations give the same results every time we run the code, which is important for reproducibility. This involves setting the seed for the standard random library, for NumPy's random number generator, and for TensorFlow's random number generator. Doing so makes random numbers, NumPy operations, and TensorFlow behaviors like neural network weight initialization deterministic. This consistency is essential for reliable debugging and for comparing results across different runs. This line checks and prints the TensorFlow version used in the script. It helps you quickly verify that the environment is set up as expected. Confirming the version is important because certain features or behaviors may only work with specific TensorFlow releases. By checking it at the start, you can avoid compatibility issues with the rest of the code. We begin by loading the MNIST dataset using the dataset tools in Keras, which provides separate training and test sets. Each set contains images of handwritten digits and their labels. The training data is used to teach the model to recognize patterns, while the test data is kept aside and used only to evaluate how well the trained model performs on new, unseen examples. This separation allows us to measure the model's accuracy and generalization ability in a more reliable way. The code first converts the training data to floating point numbers, so the pixel values match what the neural network expects. It then normalizes these values by dividing by 255, which scales them to a range between 0 and 1. This consistent scaling helps the model learn more effectively. The same conversion and normalization are applied to the test data, so both training and testing inputs are on the same scale. We add a new axis to the end of the training and test datasets to prepare them for convolutional layers. These layers expect input data to include a channel dimension. Since MNIST images are grayscale, we introduce a single channel to represent this. This adjustment ensures the image data has the correct shape for the convolutional network to process. To speed up training, we limit the dataset to 4,000 training samples and 1,000 validation samples. We create a smaller training set by taking the first 4,000 examples from the original training data, along with their corresponding labels. This reduced dataset is easier and faster to work with, while still being large enough to produce meaningful training results. We create a validation set by taking a slice of the training data. Specifically, we select a block of training images starting at the index equal to the number of training samples and ending at the index equal to the number of training plus validation samples. We take the labels from the same index range so they match the selected images. This validation set is then used to check how well the model performs on data it has not directly trained on, which helps reduce overfitting. Before building the model, the code prints the shapes of the training and validation subsets to confirm that the data is correctly split and formatted. Checking the training shape verifies how many samples there are and their dimensions, which is important for defining the input layer. Printing the validation shape confirms that this subset is also correctly sized and ready for evaluation. This quick check helps catch data preparation problems early before moving on to model construction. We build a simple convolutional neural network using a sequential model in Keras for MNIST image data. It starts with a two-dimensional convolutional layer with 16 filters of size 3 by 3 and a ReLU activation, taking input images of 28 by 28 pixels with one channel. A max pooling layer with a 2 by 2 window then reduces the spatial size of the feature maps. These feature maps are flattened into a one-dimensional vector and passed to a dense layer with 32 units and ReLU activation. Finally, a dense output layer with 10 units and a softmax activation produces class probabilities for the 10 MNIST digits, allowing the model to make predictions. The model is now being compiled, which means it is being set up for training. It uses the Atom Optimizer, a common and efficient choice for training large and complex neural networks. The loss function is sparse categorical cross-entropy, which is appropriate for multi-class classification when the labels are given as integers. During training, the model will also track accuracy as a metric, so we can monitor how well it is learning to make correct predictions. We compare two batch sizes during training to see how they affect learning. A smaller batch size of 16 means the model updates its weights after processing 16 samples, while a larger batch size of 128 processes more samples before each update and can make training faster but with fewer updates. We also train for 5 epochs, so the model goes through the entire dataset 5 times. This setup lets us observe how changing the batch size influences the training process over the same number of passes through the data. We train the model by calling its fit function with a subset of images and their labels, using a small batch size so the weights are updated more frequently within each epoch. The number of epochs is set in advance, meaning the model will pass over the entire training set that many times. We also provide validation data so the model can check its performance on unseen examples after each epoch. The training output is silenced by setting the verbosity to 0, which keeps the console clear while we observe how the model behaves with smaller batches over the fixed number of epochs. We now retrain the model using a larger batch size while keeping the number of epochs the same. The model is fit on the smaller training dataset and labels, but it processes more samples at once in each training step. The total number of passes through the dataset does not change, and we still use validation data to check performance on unseen examples after each epoch. Training runs silently with no progress messages. This setup lets us compare how changing the batch size affects the training results. This function, called summarize run, reports the final training and validation results from a model's history. It takes the last recorded training loss and accuracy, as well as the last validation loss and accuracy from the history object. It then prints these 4 metrics together in a single, clearly labeled line that includes the given name. Each value is rounded to 3 decimal places to make the output easy to read and interpret. The code prints a message to tell you that it is about to compare model training results using 2 different batch sizes. This message prepares you for the next output by clearly stating the purpose of the comparison. It signals that the following results will show how the model's performance changes when the batch size is varied. In short, it sets the context so you know what to look for in the upcoming results. We use a function called summarize run with the label small batch size and the training history from the model that used this smaller batch. The function pulls out the final training and validation loss and accuracy from the history data. It then prints these values in a clear formatted line. This gives us a quick summary of how well the model performed when trained with a small batch size. We now call a summary function to review the training results for the model that used a large batch size. This function takes a descriptive name for the run, in this case, large batch size, and the history object produced during training. The history object stores metrics such as loss and accuracy for each epoch. Using this information, the function prints the final training and validation loss and accuracy, giving a concise overview of how well the model performed with the larger batch size. This script shows how different batch sizes affect training a simple convolutional neural network on a small subset of the MNIST dataset. After setting a reproducible environment and preparing the normalized data, it builds a basic model with convolutional and dense layers and trains it twice, once with a small batch size of 16 and once with a larger batch size of 128, each for 5 epochs. It then compares the final training and validation losses and accuracies for the 2 runs. The results illustrate that batch size influences convergence and final accuracy, with smaller batches giving more detailed weight updates and often better generalization, while larger batches may train faster but can be more prone to overfitting. Choosing validation inputs. When setting up a training run, it is important to choose validation data carefully because it determines how reliably you can judge your model's ability to generalize. The validation set should look like the real-world data the model will see, but it must remain separate from the training data to avoid biased results. This usually means reserving part of your labeled data for validation or using a validation split already defined in your pipeline. The key goal is to have realistic, independent validation inputs so that performance metrics reflect how the model will behave on truly new data, rather than how well it memorized the training set. When setting up validation data for model training, you must consider how the dataset is structured and how large it is. With smaller, well-shuffled, and independent datasets, you can either use a separate validation set or reserve a fraction of the training data for validation. However, for time-ordered or session-based data, you should build a validation set that respects the sequence, such as training on earlier data and validating on later data. This way, validation scores better reflect real-world performance and avoid being unrealistically optimistic. When using data generators for training and validation, it is important to handle both streams consistently. Apply the same basic preprocessing, such as normalization, to training and validation data, but avoid random augmentations in the validation stream because they can distort your evaluation. For instance, you might use flips or other transformations only on training images, while leaving validation images unchanged to measure true performance. In imbalanced classification, keep the natural class distribution in the validation data, even if you rebalance classes during training. This careful setup gives you stable validation metrics that help you decide when to stop training and how to adjust hyperparameters. Python code. Choosing validation inputs. This script demonstrates how to choose validation inputs when training a model. It compares using a built-in validation split with providing explicit validation data. To keep the process fast and simple, it works with a very small subset of the MNIST dataset. The focus is on understanding the difference between these two ways of specifying validation data rather than on full-scale training. A line that begins with an exclamation mark is a shell command used to install a specific TensorFlow version, in this case, version 2.20.0. It is not Python code, but a command that makes sure the required TensorFlow version is available before the script runs. Specifying the version is important because different TensorFlow versions can change features and behavior. This helps keep the code consistent and compatible with the rest of the project. We start by importing several key Python modules for our work. The operating system module lets us interact with the system environment, and the random module allows us to generate random numbers, for example, to shuffle data. We then import NumPy for efficient numerical computing with arrays and mathematical operations. Finally, we bring in TensorFlow, which we will use to build and train our machine learning models and which forms the core of this script. We start by setting a seed value, such as 42, so that all random operations give the same results every time we run the code. We set this seed for the standard random library, for NumPy, and for TensorFlow, so that each of their random number generators behaves consistently. This controls randomness in things like generating numbers or initializing neural network weights. Having this deterministic setup is important for reproducibility, debugging, and fairly comparing results across different runs. This line displays the version of TensorFlow currently in use. It lets you quickly verify that your environment is running the expected version of the library. This check is important to ensure compatibility with your code and to help with debugging when issues arise. The code uses TensorFlow to check whether any physical GPUs are available on the system. If it finds at least one GPU, it sets the device type to GPU so computations can run there for faster performance. If no GPUs are detected, it automatically falls back to using the CPU instead. This ensures the program can always run with a preference for GPU when possible. This line of code displays whether the script will run on a graphics processor or on the main processor. It relies on a device choice made earlier in the program and simply reports that choice. This information tells the user what hardware is being used, which can affect how fast model training runs. This code uses TensorFlow's Keras tools to load the MNIST dataset, a standard collection of handwritten digit images used for image processing tasks. It retrieves only the training portion of the data, separating the images from their labels. The images hold the pixel data, while the labels indicate which digit each image represents. This separation prepares the data so a model can be trained and later evaluated effectively. The code processes the MNIST training images by converting their pixel values to floating point numbers, and then normalizing them. Each pixel is divided by 255 so that all values fall between 0 and 1. This normalization step puts the input data on a consistent scale, which helps neural networks train more effectively and converge faster. We add an extra dimension to the training data to represent channels, because convolutional layers in neural networks require inputs with a specific shape that includes this channel dimension. For grayscale images, like those in the MNIST dataset, there is only one channel. By using a function that expands the array dimensions, we give each image this additional channel dimension. This adjustment makes the image data compatible with the convolutional layers used later in the model. The code first prints the shape of the training data to verify that its dimensions match what we expect. This quick check confirms that the data has been loaded correctly and that any pre-processing steps have worked as intended. By validating the dataset's shape before splitting it, we reduce the risk of errors later in the workflow. This simple step helps ensure the data is ready for further analysis or model training. To keep the training process fast, the code uses only a small subset of the MNIST training data. It limits the dataset to 6,000 samples by taking just the first 6,000 images and their corresponding labels. This slicing of the original training arrays reduces the amount of data the model has to process, which shortens the overall runtime while still allowing the training procedure to run. The code checks that the subset of training data has the expected size by printing the number of samples it contains. It does this by reading the first value of the data array's shape, which represents how many examples are included. This verification step helps confirm that the subset was created correctly and that the data is properly prepared for the next stages of processing. We build a simple convolutional neural network for image classification using the Keras sequential interface. It starts with a two-dimensional convolution layer with 8 3x3 filters and a ReLU activation, taking grayscale images of 28 by 28 pixels as input. A max pooling layer with a 2x2 window then reduces the spatial size of the feature maps. These feature maps are flattened into a one-dimensional vector and passed to a dense layer with 32 units and ReLU activation. The final output layer is a dense layer with 10 units and a softmax activation, producing a probability distribution over the 10 image classes. The model is compiled using the Atom optimizer, which is commonly used because it trains neural networks efficiently and adapts during learning. It uses sparse categorical cross-entropy as the loss function, which is appropriate for multi-class classification when the target labels are integers. The model also tracks accuracy as a metric, so we can monitor how well it is performing during training. We train the model using the Keras fit method on the MNIST images and their labels. The model processes the data in batches of 64 samples and updates its weights after each batch. Training runs for 3 full passes over the dataset, called epochs. We reserve 20% of the training data for validation to monitor performance, and we shuffle the data before each epoch to improve generalization. The training runs silently with no progress messages shown. To create explicit validation data, we first compute the validation size as 20% of the subset size, which tells us how many samples to reserve. We then take the last portion of the training inputs and the corresponding labels, using this validation size to slice them out. These extracted samples form the validation set, while the remaining data stays as the training set. This separation lets us evaluate the model on data it has not seen during training. The code selects the training portion of the MNIST dataset by slicing off the last part, which has been set aside for validation. It applies this slicing to both the input images and their labels, so they stay correctly matched. This ensures the model is trained only on data that is separate from the validation set. As a result, the model's performance can be evaluated on the validation data, without bias from having seen it during training. The code prints the size of the training dataset to verify that the split between training and validation data is correct. By checking this number, we can confirm that the data has been divided as intended. This simple check helps ensure consistency in the data split, which is important for maintaining the integrity of the model training process. We build a new sequential model in Keras to match the previous setup and allow a fair comparison. It starts with a 2-dimensional convolutional layer that has 8 filters of size 3 by 3 with a ReLU activation, and it takes grayscale images of size 28 by 28 as input. This is followed by a max pooling layer with a 2 by 2 window to reduce the spatial dimensions. The result is then flattened into a 1-dimensional array and passed to a dense layer with 32 units and ReLU activation to add nonlinearity. Finally, a dense output layer with 10 units and a softmax activation produces class probabilities for the 10 MNIST digits. The code compiles the second model using the same configuration as before. It chooses the Atom optimizer for efficient and adaptable training. The loss function is sparse categorical cross-entropy, which is appropriate for multi-class classification when the labels are integers. The model is set to track accuracy as the main metric for evaluating performance during training. We train the model by calling the fit method with training inputs and labels, using a batch size of 64 for 3 training passes. Instead of relying on an automatic validation split, we explicitly provide validation inputs and labels as a separate tuple. We turn off shuffling to keep the data order fixed, and set the training to run silently without printed output. This setup lets us directly compare the effect of using explicit validation data versus using a validation split. The code first reads the final validation accuracy from the training run that used a validation split, by taking the last recorded validation accuracy value from the training history. It then repeats this process for the training run that used a separate, explicit validation dataset. By extracting the final validation accuracy from both histories, it becomes possible to directly compare how well each training strategy performed on validation data. The code reports the final validation accuracy obtained using the validation split approach and presents it in a compact form. It rounds the accuracy value to 4 decimal places to keep the result clear and precise. This formatting makes it easier to compare that accuracy with results from other validation strategies. We report the final validation accuracy using the explicit validation data method. To do this, we take the stored accuracy value for the validation set and print it out. The value is rounded to 4 decimal places, so the result is both clear and precise in the output. The message explains that using a validation split is appropriate only when your data is well shuffled and follows an independent and identically distributed pattern. In other words, it works best when the data points are randomly ordered and statistically similar. For structured or non-random data, it is safer to create an explicit validation set. This more deliberate separation of training and validation data provides better control and can lead to more reliable evaluation results. This script compares 2 ways of using validation data when training a simple convolutional neural network on a subset of the MNIST dataset. In the first approach, it relies on a validation split, where a portion of the training data is automatically held out for validation. In the second approach, it manually separates the data into training and validation sets and trains an identical model using this explicit validation data. Both models are trained for 3 epochs, and their final validation accuracies are compared. The results show that a validation split works well for well-shuffled, independent, and identically distributed data, while an explicit validation set can be more suitable for structured datasets, offering insight into when each method is most effective. Shuffling and class weights. When setting up a training run, it is important to decide whether and how to shuffle your data between epochs. Shuffling changes the order of examples each time the model sees the dataset, so each mini-batch better reflects the overall data distribution. If the data is ordered by time, location, or class label, and you do not shuffle, early batches may be dominated by one pattern, leading to overfitting and poor convergence. For example, with medical data grouped by hospital, the model might mostly learn from a single hospital if the data is not shuffled. By shuffling, you create more balanced batches, which leads to smoother learning and more reliable training behavior. Shuffling interacts closely with how we handle class imbalance using class weights. In problems like fraud detection or rare disease diagnosis, the positive class is much less common, so a model can appear accurate while failing on these rare cases. Class weights address this by making mistakes on minority examples count more during training, so the model pays more attention to them. When this weighting is combined with shuffling, the model is better able to learn decision boundaries that fairly represent both majority and minority classes, rather than focusing mainly on the most frequent class. When training on structured or sequential data, it is important to manage both shuffling and class weights carefully. In time series tasks, you keep the order within each sequence, but shuffle the sequences between epochs, so temporal patterns are preserved while the model still sees varied batches. If the data is imbalanced, you assign higher weights to rare sequences so they have a stronger effect on learning. Shuffling then mixes common and rare sequences, while class weights boost the impact of the rare ones. Together, these choices create better training conditions and improve the model's generalization and reliability on the most important outcomes. Python code, shuffling, and class weights. This script demonstrates how to use shuffling and class weights on a small, imbalanced dataset. It is designed to run quickly so you can see the effect of these techniques without long processing times. The output is kept minimal, focusing only on the key results needed to understand how shuffling and class weighting work in this simple example. The line that begins with an exclamation mark is a shell command used to install TensorFlow version 2.20.0, not a piece of Python code. It makes sure that this exact version of TensorFlow is available before the script runs. This matters because different TensorFlow versions can change features and behavior. By specifying the version, you help keep the code consistent and compatible across different environments. We begin by importing a few key libraries needed for our script. We include a library for interacting with the operating system, one for generating random numbers and controlling reproducibility, and a numerical computing library for working with arrays and mathematical operations. We also import a machine learning library used to build and train models. Together, these imports provide the basic tools required for data manipulation and model training in our code. To make code produce the same results every time it runs, we set a fixed seed value, such as 42, for all random number generators we use. We first set the seed for Python's built-in random functions, then for the random number generator in NumPy, and finally for TensorFlow's random processes, including weight initialization. Using the same seed across these libraries makes all random outputs reproducible. This deterministic setup is important for debugging and for reliably comparing results between different runs of the code. This code displays the version of TensorFlow that is currently in use. Knowing the exact version helps you check compatibility with other tools and libraries. It also lets you understand which features, changes, or improvements are available in your environment. In short, printing the TensorFlow version is a quick way to confirm what capabilities you can rely on. We start by loading the MNIST dataset using the Keras tools in TensorFlow. MNIST is a standard collection of handwritten digit images used to train and test image recognition models. The data is divided into training images and labels, and separate testing images and labels. This split lets us train the model on one part of the data and then evaluate how well it performs on new, unseen examples, which helps check that it generalizes rather than just memorizing the training set. To speed up training, the code uses a smaller subset of the data instead of the full dataset. It takes only the first 6,000 training images and their matching labels. This reduced dataset allows the model to train faster and complete more iterations in less time. As a result, it becomes easier to experiment and test how well the model performs without the cost of processing all available data. To create imbalanced binary labels, we first choose the minority class and assign it the value 1. We then compare each training label to this minority class, producing a true or false result for each example. These Boolean values are converted to integers, so the minority class becomes 1 and all other classes become 0. This process yields a binary imbalanced dataset that highlights the minority class. To check for class imbalance in a dataset with binary labels, we use a function from the numerical library to list all unique label values and count how many times each one appears. This tells us how many samples belong to each class. We then display these counts as a dictionary so we can clearly see the class distribution. From this, we can quickly determine whether one class has significantly more samples than the other. To prepare the training images for a neural network, each pixel value is divided by 255 so that all values fall between 0 and 1, which helps the model train more effectively. After this scaling, an extra dimension is added to each image so that its shape becomes 28 by 28 by 1. This added channel dimension is required because convolutional layers in TensorFlow expect input data to include a channel, even for grayscale images with only a single channel. Before building the model, the code first prints the shapes of the training data and the binary labels to confirm they are correctly set up. This check makes sure that each image has a matching label and that their dimensions are compatible. Verifying this alignment is essential because if the data and labels do not match, the model cannot be trained properly. We build a small sequential model in TensorFlow Keras for binary image classification. It takes 28 by 28 grayscale images as input, then applies a two-dimensional convolutional layer with 8 filters and a rectified linear activation to extract features. A max pooling layer downsamples these feature maps, and the result is flattened into a one-dimensional vector. This vector passes through a dense layer with 16 units and rectified linear activation for further processing. Finally, a single unit dense layer with a sigmoid activation outputs a probability that the input image belongs to the positive class. The model is now being compiled, which prepares it for training. It uses the Atom optimizer, a common choice because it adjusts learning rates efficiently. The loss function is binary cross-entropy, which is appropriate for binary classification and measures how well the model is doing. During training, accuracy is tracked as a metric to show how often the model's predictions are correct. To address class imbalance, we first count how many negative and positive samples we have. We then compute a weight for each class by taking 1 divided by its sample count, multiplying by the total number of samples, and then dividing by 2. This gives a separate weight for the negative and positive classes. Finally, we store these values in a dictionary that maps each class to its weight, so that both classes have a more balanced influence during model training. The code prints the class weights that were calculated for the dataset, which are used to handle class imbalance during training. Seeing these values lets you confirm that the weights were computed correctly and understand how they will affect learning. This check is important to help prevent the model from becoming biased toward the majority class. We train the TensorFlow model on images with binary labels using a fit function that runs for 3 epochs, meaning it passes over the entire dataset 3 times. The data is processed in batches of 64 samples before the model updates its weights, and the samples are shuffled each epoch to avoid learning accidental patterns. To handle class imbalance, we apply class weights so the minority class has more influence during training. We also set aside 20% of the data for validation to track performance on unseen examples, and we turn off detailed logging to keep the training process quiet and focused. To evaluate the model after training, we look at 4 final metrics from its history. We take the last recorded training loss and the last validation loss, which show how well the model fits the training data and how it performs on unseen validation data. We also take the final training accuracy and final validation accuracy, which indicate how often the model predicts correctly on each set. Together, these values summarize the model's performance on both training and validation data at the end of training. The code prints a brief summary of how the model performed during training. It reports the final training loss and validation loss, each rounded to 3 decimal places, to show how well the model fits the training data compared with unseen validation data. It then prints the final training accuracy and validation accuracy, also rounded, to indicate how often the model predicts correctly on both sets. Together, these values provide a quick overall view of the model's performance and generalization. This script shows how to handle an imbalanced dataset in TensorFlow using a small subset of the MNIST digits. It converts the labels to a binary problem focused on the digit 1, creating a strong imbalance between the positive and negative classes. Then normalizes and reshapes the images for a simple convolutional neural network. The model is trained with binary cross-entropy loss and class weights that give extra importance to the minority class. After 3 training epochs, with shuffling and class weights applied, the script reports the final training and validation loss and accuracy, demonstrating improved performance on the minority class compared with unweighted training. Keras training callbacks, tuning early stopping. Early stopping is a technique that monitors a metric like validation loss or accuracy during training and stops the process when additional epochs no longer bring real improvement. It helps prevent overfitting, where the model starts memorizing noise or quirks in the data instead of learning general patterns. This is especially important with noisy or limited data, such as in predicting hospital readmissions. The key idea is to find a balance between training long enough for the model to learn well, but not so long that it begins to overfit. In early stopping, you mainly choose what performance metric to monitor, how much patience to allow, and what minimum change counts as real progress. For regression, you might track validation loss, while for classification, you might use validation accuracy, or AUC. Patience controls how many training steps you wait after the last improvement before stopping, where too little can stop learning too soon, and too much can waste time. The minimum change, or delta, sets the smallest improvement you consider meaningful, so you can ignore random noise. By tuning these settings together, you can adapt early stopping to the behavior of your specific dataset and problem. When tuning early stopping, focus on the training and validation curves and balance training time against performance gains. For small, low-cost projects, you can allow more epochs with higher patience and a small required improvement. For large, expensive models, use a larger required improvement and shorter patience to save resources. If the validation metric is noisy, increase both patience and the improvement threshold to avoid stopping too early. With practice, you will learn to choose settings that capture the best model without wasting computation. Python code, tuning early stopping. This script shows how to tune early stopping during training. It works on a very small subset of the MNIST dataset, so it runs quickly. The training process is kept simple, and the output is concise, making it easier to see how early stopping behaves. The line with the exclamation mark is a command that installs TensorFlow version 2.20.0. Specifying this exact version makes sure the script uses the expected features and behaves consistently. This practice helps avoid problems that can occur when a library is updated and its behavior changes. This script begins by importing the operating system module to work with files and environment settings, and the random module to generate random numbers, such as for shuffling data. It then imports NumPy, a library for efficient numerical computations with arrays and matrices. Finally, it brings in TensorFlow, a widely used library for building and training machine learning models, including neural networks and other advanced techniques. We begin by setting a seed value of 42 so that any random operations give the same results every time we run the code, which is important for reproducible experiments. To do this, we set the seed in the random library, then in the NumPy random number generator, and finally in TensorFlow's random operations. Using the same seed across these libraries makes the overall behavior of our code deterministic and consistent. This line displays the version of TensorFlow currently in use. It helps you quickly verify that the correct version of the library is installed. Confirming the version is important to ensure compatibility with your code and to help with debugging when issues arise. The code first checks whether any GPUs are available by asking TensorFlow for a list of physical GPU devices. If it finds at least one GPU, it sets the model to run on the GPU so computations are faster. If no GPU is found, it automatically falls back to using the CPU instead. This approach ensures the model always uses the most efficient hardware available on the system. The code prints a message indicating whether computations will primarily run on a GPU or on the CPU. It makes this choice based on an earlier check for available physical GPUs. If at least one GPU is found, it uses the GPU. Otherwise, it falls back to the CPU. Knowing this helps you understand the hardware context for training the model, which can greatly affect performance and speed. We begin by loading the MNIST dataset using the Keras tools in TensorFlow. MNIST is a standard collection of handwritten digit images used to train and test image processing models. The data is divided into a training set, which is used to teach the model, and a testing set, which is used to measure how well it performs. Each part contains images of digits, along with labels that indicate the correct number for each image. The code prepares the training and test images by converting their pixel values to floating point numbers and scaling them to fall between 0 and 1. It does this by dividing each pixel value by 255, which is the maximum value in an 8-bit image. Normalizing the data in this way helps the neural network train more effectively and remain more stable during learning. To prepare image data for a convolutional neural network, we need to add a channel dimension to both the training and test sets. We do this by expanding the shape of the data arrays so that a new dimension is added at the end. This extra dimension represents the image channels and is required for the two-dimensional convolution layer to process the images correctly. In this case, it ensures that each image is treated as a single-channel grayscale image, as is typical for datasets like MNIST. Before training the model, the code checks that the number of training images matches the number of training labels, so that every image has a correct label, which is essential for supervised learning. It performs the same check for the test images and test labels to keep the test data consistent. These checks act as safeguards that catch mismatches early and help prevent errors during training or evaluation. To speed up training, we work with a smaller subset of the data. We limit the training set to 800 samples and the validation set to 200 samples. To create the reduced training set, we simply take the first 800 examples from the original training data, along with their corresponding labels. This gives us a smaller, faster data set while keeping the structure of the original data and labels aligned. To create a validation split from the training data, we reserve a portion of the training images and their corresponding labels for validation. We select a slice of the training images based on the desired number of training and validation samples, and take the matching slice from the labels so they stay aligned. This reserved subset becomes our validation set, which we then use to check how well the model performs on data it has not directly learned from during training. We build a simple convolutional neural network using a sequential model. It starts with a two-dimensional convolutional layer with 16 filters of size 3 by 3, using ReLU activation and taking 28 by 28 grayscale images as input. This is followed by a 2 by 2 max pooling layer to reduce the spatial size of the feature maps. Then a flattening step that converts the pooled feature maps into a one-dimensional vector. We then add a dense layer with 32 units and ReLU activation. And finally, a dense output layer with 10 units and a softmax activation that produces class probabilities for the 10 MNIST digits. The model is compiled with settings that prepare it for training a multi-class classifier. It uses the Atom optimizer, which is efficient and adapts well during training. The loss function is sparse categorical cross-entropy, which is appropriate when class labels are given as integers. Accuracy is used as the main metric to track how often the model's predictions match the true labels during both training and validation. We set up an early stopping callback in TensorFlow Keras that watches the validation loss during training and stops training if it does not improve. The patience is 2 epochs, so training ends after 2 rounds with no meaningful improvement. A minimum change of 0.001 in validation loss is required to count as an improvement. When training stops, the model automatically restores the weights from the epoch with the best validation loss. We use a stricter early stopping callback in TensorFlow Keras that watches the validation loss during training and stops if it does not improve enough. Specifically, if the validation loss fails to get at least 0.01 better for one epoch in a row, training ends early. This behavior is controlled by setting the patience to 1 and the minimum required improvement to 0.01. At the end of training, the model automatically restores the best weights it achieved, so it keeps its strongest performance. We train the model using a baseline early stopping strategy by calling its fit method on a small subset of training images and labels, along with a separate validation subset. Training can run for up to 20 epochs, but early stopping monitors the validation loss and stops the process if it no longer improves. The model updates its weights in batches of 64 samples at a time. Detailed training output is turned off to keep the logs concise. To find out how many epochs the model actually trained before early stopping, we look at the training history. Specifically, we check how many loss values were recorded during training. The length of this loss history tells us the number of completed epochs. This shows exactly when early stopping halted the training process. To fairly compare different early stopping strategies, we first reset the model by cloning its architecture to create a fresh version with untrained weights. We then rebuild this new model using the same input shape as the original. After that, we compile it with the Atom optimizer, use sparse categorical cross-entropy as the loss function, and track accuracy as the main metric. This prepares a clean, consistent setup for training the model under stricter early stopping conditions. We train the model on the smaller training set with its labels and monitor performance using separate validation data. Training can run for up to 20 epochs, but strict early stopping will halt it sooner if the validation loss does not improve enough. We use a batch size of 64, meaning the model updates its parameters after processing that many samples at a time. A strict early stopping callback is included to enforce this stopping rule, and detailed training output is turned off to keep the process quiet. To find how many epochs the model trained under the stricter early stopping rule, we look at the training history it recorded. Specifically, we examine the list of loss values saved during training. The length of this loss history tells us how many epochs were actually completed. This number reflects the point at which early stopping halted further training. We limit the test set to 500 samples, so we can evaluate the model on a smaller, more manageable portion of the data. To do this, we take only the first 500 test images and use them to create a reduced test dataset. We then take the matching 500 test labels so that each image still has the correct label. This setup lets us test the model quickly while keeping the inputs and outputs properly aligned. We now evaluate the model that was trained using the baseline early stopping approach on a small test subset. To do this, we run its evaluation procedure on test images and their corresponding labels. The evaluation is performed quietly, without detailed printed output. This process provides the model's loss and accuracy on the test set, which we use to assess its performance. We now evaluate the model that was trained with stricter early stopping to see how well it performs on unseen data. Using the evaluation function from the Keras API, we test the model on a small portion of the test images along with their labels. The evaluation runs quietly, with detailed output turned off, and returns performance metrics. This step shows how well the stricter early stopping model generalizes beyond the training data. We first report how many epochs the model trained under the baseline early stopping strategy to see when training stopped. We then do the same for the stricter early stopping strategy, so we can compare how different patience levels changed the training duration. Next, we show the test loss and test accuracy for the baseline model, rounded to 4 decimal places to measure its performance on unseen data. Finally, we present the test loss and accuracy for the model trained with stricter early stopping, allowing a direct comparison of which strategy produced better test performance. This script shows how changing early stopping settings affects training a convolutional neural network on a small part of the MNIST dataset. It compares a baseline early stopping strategy with a patience of 2 epochs to a stricter strategy with a patience of 1 epoch, both based on validation loss. The model is trained separately with each strategy, and the number of epochs before training stops is recorded. Afterward, both models are evaluated on a small test set, and their test loss and accuracy are printed. The results illustrate that stricter early stopping usually ends training sooner and can lead to slightly different test performance compared with the baseline. Checkpoint paths and formats. When saving model checkpoints during training, it is important to choose a reliable storage location and a clear file naming scheme. Use a dedicated folder for each experiment so files are not overwritten, and resuming training is straightforward. Within that folder, name checkpoints descriptively, for example by including the training epoch or a timestamp, so you can easily tell which stage they represent. This organization is especially helpful in sensitive applications like medical imaging, where you need to quickly and confidently restore the best model. Choosing the right checkpoint format matters because it determines what is saved and how easily a model can be reloaded in different environments. Some formats store only the learned weights, which is fine if you know the model architecture and settings will stay the same. Other formats store the entire model, including its structure and training configuration, creating a complete package that can be reused without rebuilding anything. This more comprehensive and portable approach is especially useful when models are trained in one place, such as powerful cloud systems, and then deployed elsewhere, like on edge servers, without losing any essential components. When managing checkpoints, make sure they fit smoothly into your workflow for versioning, storage, and collaboration. On shared systems, store them in organized project folders with clear subfolders so you can link each checkpoint to its datasets, configurations, logs, and results. In storage-limited environments, keep only the best-performing checkpoints and remove older ones. In high-stakes industries like autonomous driving, use well-documented paths and formats so you can always trace which model version produced a given prediction. Python code, checkpoint paths, and formats. This short script demonstrates basic use of Keras checkpoints, with an emphasis on how to set up paths and choose file formats for saving models. It is designed to be run step by step in a Colab notebook. By following the cells in order, you can see how checkpoints are created and managed during training. The script includes an optional command to install TensorFlow using pip, which is commented out so it does not run automatically. You should run this command yourself only if TensorFlow is not already installed on your system. The command specifies TensorFlow version 2.20.0 to match the requirements of the rest of the script and ensure compatibility. We start by importing the operating system library so we can work with file paths and directories. We also import the pathlib library, which lets us handle file system paths in a more intuitive, object-oriented way. Finally, we bring in the random library to generate random numbers, which is useful for setting seeds or creating random data samples. We start by importing TensorFlow, a main library used for machine learning and deep learning. Within TensorFlow, we use Keras as a high-level interface that makes it easier to build and train neural networks. We then import the layers tools from Keras, which provide common components like convolutional and dense layers. Together, these imports prepare the environment so we can efficiently create and train neural network models. We begin by setting a fixed random seed with the value 42 so that any random operations in our code always produce the same results. This step is important for reproducibility, meaning we can reliably repeat experiments and get identical outcomes. By using the random library to set this seed, all later random number generation becomes consistent across different runs of the program. We set the random seed in TensorFlow so that any operation involving randomness gives the same result every time the code runs. This makes our experiments reproducible, which is especially important when training models. By fixing the seed, we can rerun the training process and reliably get consistent outcomes across different runs. This code displays the version of TensorFlow currently in use. Knowing the exact version helps you check compatibility with your project and other libraries. It also tells you which features and syntax are available, since different TensorFlow versions can behave differently. We begin by loading the MNIST dataset using Keras, which is a standard collection of handwritten digit images used to train image recognition models. The loading function returns 2 pairs of data, 1 pair for training and 1 pair for testing. Each pair includes the images and their corresponding labels. This built-in separation into training and test sets is important because it lets us train the model on one portion of the data and then fairly evaluate its performance on a separate, unseen portion. To speed up training, we work with a smaller subset of the data instead of the full dataset. We choose to use 4,000 samples, and then restrict the training data to just these first 4,000. This reduces computation time and allows us to iterate and test the model more quickly. Once the approach works well on this subset, we can later scale up to the full dataset if needed. The code selects a smaller set of training labels from the MNIST dataset by taking the first 4,000 labels. This matches the previously chosen subset of 4,000 training images. By doing this, each reduced image still has the correct label. This step keeps the training data consistent and reliable while working with a smaller dataset. The code first converts the training images so that each pixel is stored as a floating point number. It then divides all pixel values by 255 to scale them into a range from 0 to 1. This normalization step is a standard part of pre-processing for neural networks and helps make training more stable and effective. We add a new dimension to the training data to represent the channel, which is required by the convolutional layer in our model. The original training images are 2-dimensional, but convolutional layers in Keras expect 3 dimensions: height, width, and channels. By adding this extra channel dimension, each image is correctly treated as a single channel image. This setup matches the typical format for grayscale images, such as those in the MNIST dataset. The code verifies that the training data contains the expected number of samples. It does this by asserting that the shape of the training data array matches the required sample count. This check helps detect unexpected changes or errors that may have occurred during data preprocessing. By validating the data setup in this way, it helps ensure the model is trained on correctly prepared data. We build a simple Keras sequential model by stacking a few basic layers. First, we use a 2-dimensional convolutional layer with 8 3x3 filters and a ReLU activation, designed for 28x28 grayscale images. The output of this layer is then flattened into a 1-dimensional array, so it can be passed to a dense layer. Finally, we add a dense layer with 10 units and a softmax activation, which produces a probability for each of the 10 MNIST classes and allows the model to make a prediction. The model is compiled using the Atom Optimizer, which is a common and efficient choice for training neural networks. It uses sparse categorical cross-entropy as the loss function, which is appropriate for classification problems with integer labels, such as the MNIST dataset. During training, the model also tracks accuracy as a metric, so we can monitor how well it is correctly classifying the input images over time. We start by creating a main directory called checkpoints example using the pathlib library, which will hold all our model checkpoint files. To make sure this directory is available, we call the method that creates it and allow existing directories without causing an error. This lets us safely set up or reuse the same location for saving checkpoints without interrupting the program. We create a dedicated subdirectory for this experiment by combining the main project folder with a specific name for this run. This gives us a clear place to store all data related to the experiment. We then make sure this folder exists, allowing the directory creation step to quietly succeed even if it is already there. This approach keeps our checkpoint files organized in a single, well-defined location for this particular run. This code prints the full directory path where model checkpoints will be saved. It converts the experiment directory to an absolute path, so there is no confusion about the storage location. This helps you confirm that checkpoints are going to the correct place, which is especially important when relative paths might be unclear in your working environment. We set up a naming pattern for checkpoint files that includes the training epoch and the validation accuracy. The epoch number is always written with 2 digits to keep file names consistent. The validation accuracy is written with 3 decimal places to record performance precisely. This structured naming makes it easy to identify, compare, and sort checkpoints by training progress and accuracy. We create a full checkpoint path in the Keras format by joining the experiment directory with a file name pattern. This pattern includes placeholders for the training epoch and the validation accuracy. The result is a single string that specifies exactly where each model checkpoint will be saved. Each saved file follows this pattern and uses the standard Keras file extension. We set up a model checkpoint callback to automatically save the best version of the model during training. It uses a file naming pattern based on the training epoch and validation accuracy, and it monitors validation accuracy to decide which model is best. By saving only when a new highest validation accuracy is reached, we keep just the top performing model. We choose to store the entire model rather than only its weights, and we use a setting that looks for the maximum validation accuracy while keeping the training output quiet. We use an early stopping callback to avoid training the model longer than necessary. It watches the validation accuracy, and if this accuracy does not improve for 2 epochs in a row, training stops. With the option to restore the best weights turned on, the model automatically returns to the best performing states seen during training. The verbosity is set to 0, so this process runs silently without printing messages. We train the model using the fit method with the training inputs and labels, running for 5 epochs, so it passes over the data 5 times. The batch size is set to 64, so the model updates its weights after every 64 samples. We reserve 20% of the training data for validation to monitor performance during training. A checkpoint callback saves the best version of the model based on validation accuracy, and an early stopping callback halts training if this accuracy does not improve for 2 epochs in a row. Detailed training logs are turned off to keep the output quiet. This code collects all checkpoint files in a given directory by searching for files that use the Keras file extension. It relies on a file matching tool from the standard library to find these files within the experiment directory. After gathering them, it sorts the list, usually by file name. This ordered list makes it easier to process the checkpoints in sequence later on. The code prints a short summary of the checkpoint files by first reporting how many were found. It does this by taking the length of the list of checkpoint files that were previously collected and sorted. This count gives a quick overview of how many checkpoints were saved during the training process. The code goes through each checkpoint file in a list and prints the name of each saved checkpoint. This creates a simple record of which checkpoints were produced during training. By reviewing this output, you can easily verify that checkpoints were saved correctly and track the model's progress over time. The code first checks whether any checkpoint files exist. If there are checkpoints, it takes the last one in the list and uses its path, converted to a string, as the location of the best saved model from training. If no checkpoint files are found, it sets the best model path to none, meaning no model was saved. The program first checks whether there is a valid path to a saved model checkpoint. If a checkpoint exists, it loads the model from that file using the Keras load model function, so the model's best saved state is restored. If no checkpoint is found, it simply continues with the current version of the model. This ensures the code always proceeds with the best available model, whether it comes from a previous training session or the most recent run. We begin by selecting a smaller subset of the test data, such as the first 1,000 samples, so we can evaluate the model more quickly. Each image in this subset is converted to floating point values, and then normalized by dividing the pixel values by 255. This scales all pixels to lie between 0 and 1. Using this consistent scale is a standard preprocessing step that helps neural networks learn and perform more effectively. We add a channel dimension to the small test images so their shape matches what the convolutional layers expect. These layers require input data that includes a channel dimension, such as for grayscale or color information. By expanding the image shape to include this dimension, we align the test data with the model's required input format. This allows the model to process and evaluate the images correctly. The code takes the first 1,000 entries from the test labels and uses this smaller group to check how well the model performs. By evaluating on a reduced test set, the process runs faster while still giving a quick indication of the model's accuracy. This approach helps make testing more efficient without running the full test set every time. Before evaluating the model, the code first checks that the number of test samples matches the number of test labels. This confirms that every test image has a corresponding label. Making sure these shapes align is essential for accurate evaluation and helps prevent errors during the testing process. The code evaluates the loaded model on a small test subset by comparing its predictions with the true test labels. It computes the loss and accuracy to measure how well the model performs. This evaluation runs silently without printing anything, and the resulting loss and accuracy values are stored for later use or display. This code reports how accurate the restored model is on the test data. After loading the model from a saved checkpoint, it calculates the test accuracy and prints a short message with the result. The accuracy is rounded to 3 decimal places to keep the output clear and easy to read. This gives a quick summary of the model's performance after being reloaded. This script shows how to use Keras to manage model checkpoints while training a simple convolutional neural network on a small subset of the MNIST dataset. The model is trained with the Atom optimizer and sparse categorical cross-entropy loss. And checkpoints are saved to a directory with file names that include the epoch and validation accuracy. Callback functions automatically save the best performing model and stop training early based on validation accuracy. After training, the script lists the saved checkpoint files, reloads the best model from the final checkpoint, and evaluates its accuracy on a small test subset. The final test accuracy confirms how checkpoints help preserve and later evaluate the best model found during training. TensorBoard training logs. TensorBoard is a key tool for visualizing deep learning training, giving you a time-based view of how optimization progresses. By adding a TensorBoard callback to your training loop, you can log metrics such as loss and accuracy for both training and validation at each epoch or batch. These logs are saved to disk and then turned into interactive dashboards in your browser, so your training behaves like a dynamic experiment notebook. This helps you see whether your model is converging properly, how validation accuracy changes over time, and how choices like learning rate schedules or architecture adjustments affect training stability, for example in tasks like medical image classification. TensorBoard is most powerful when you use it to track many aspects of training and compare different runs in a structured way. Besides basic metrics, you can log learning rates, custom metrics, and histograms of weights and activations. By pointing TensorBoard to a directory with logs from multiple experiments, you can overlay their curves to see which configuration converges faster or generalizes better. This makes it much easier to spot setups that overfit or maintain a healthy performance gap, reducing trial and error in real-world tasks like tuning a recommendation system. TensorBoard works alongside callbacks like early stopping and model checkpointing by showing you visually what they are doing during training. When early stopping halts training, you can see exactly where the validation loss stopped improving, which helps you adjust patience settings in future runs. Checkpoint visualizations reveal which epoch produced the best weights and whether training could have been shorter. They can also show if performance jumps followed a learning rate change, confirming whether your schedule is effective. Across applications such as speech recognition and financial forecasting, this makes training decisions more transparent and grounded in clear visual evidence. Python code, TensorBoard training logs. This script demonstrates how to view training logs in TensorBoard using a very small model and dataset. It is designed as a simple practice tool rather than a full application. For the best experience, run it in Google Colab, where everything is already set up for you. Use it to get comfortable with how TensorBoard displays training progress. The commented line recommends installing TensorFlow version 2.20.0 to match what the script expects. Using this exact version helps avoid compatibility issues. It ensures the code can access the specific features and behaviors it was written for. In short, it is a setup step to prepare the environment correctly before running the program. We start by importing 3 key tools. The operating system module lets us work with the file system, for example, to create folders or manage file locations. The datetime module helps us handle dates and times, which is useful for adding timestamps to logs or files. Finally, we import the numerical computing library NumPy, which we will use for tasks like setting random seeds and working with arrays. We start by importing TensorFlow, a library used to build and train machine learning models. From TensorFlow, we then import Keras, which offers a simpler, high-level way to define neural networks. Using Keras on top of TensorFlow lets us create models more intuitively while still relying on TensorFlow's powerful features behind the scenes. To make our code produce the same results every time it runs, we set deterministic random seeds. We first set the seed in the numerical library to 7, so that any random operations there behave consistently. We then set the TensorFlow seed to 7 as well, which makes random processes like weight initialization and data shuffling repeatable. This practice improves the reproducibility of our experiments, making it easier to debug and compare different runs. This line displays the version of TensorFlow currently in use. Knowing the exact version helps you check compatibility with your code and other libraries. It is also useful for debugging, because different TensorFlow versions can change features or behavior. By printing the version, you can quickly confirm that your environment matches what your project expects. The code first checks whether any GPUs are available by asking TensorFlow for a list of physical GPU devices. If it finds at least one, it sets the model to run on the GPU, so computations are faster. If no GPU is detected, it automatically falls back to using the CPU. This setup lets the model take advantage of GPU acceleration when possible, while still working correctly on systems without a GPU. The code prints a message indicating whether computations will primarily run on a GPU or on the CPU. This choice is made earlier by checking if any physical GPUs are available. If a GPU is found, it is selected. Otherwise, the system falls back to the CPU. Knowing which device is used helps you understand the hardware context, which can affect performance and training speed. The code uses Keras to load the MNIST dataset, which is a standard collection of handwritten digit images for training image processing models. It provides one set of images and labels for training, and another separate set for testing. This separation lets you train the model on the training data and then evaluate how well it performs on new, unseen test data. In this way, you can check how well the model generalizes beyond the examples it was trained on. To speed up training, we work with a smaller subset of the data instead of the full dataset. We use 4,000 samples for training and 1,000 samples for testing. This makes it faster to train and evaluate the model. It is especially useful when we are experimenting or practicing and do not need to use all available data. In this step, we limit the training data to only a subset of the available samples. We take the first 4,000 examples from both the input features and their corresponding labels. Using this smaller portion of the dataset speeds up training and makes it easier to run quick experiments. This approach is especially helpful when computational resources are limited or when we want faster feedback during model development. We now limit the test dataset to a fixed number of samples. Specifically, we select the first 1,000 test images and their matching labels. This creates a smaller, more manageable test set. It also keeps the test data consistent with the reduced subset size we use during training. To prepare the images for a neural network, the training data is first converted to floating point numbers, so it works correctly with later operations. Each pixel value is then divided by 255, which rescales the data to range between 0 and 1. This normalization helps make training more stable and efficient. The same scaling is applied to the test images to keep the training and testing data consistent. To prepare image data for a convolutional neural network, we need to add a channel dimension to both the training and test sets. This is done by using a function from the numerical library that expands the array dimensions by adding a new axis at the end. Adding this channel dimension is essential because convolutional layers in TensorFlow expect inputs to include it, even when there is only one channel for grayscale images, such as those in the MNIST dataset. Before building the model, the code prints the shapes of the training data and labels to verify that their dimensions are correct. This check confirms that the data matches the model's expected input format. By doing this early, you can detect any mismatches between data and labels and avoid errors during model training. We build a simple convolutional neural network using a sequential model for classifying MNIST digits. It starts with a two-dimensional convolutional layer with 8 3x3 filters and ReLU activation, taking 28 by 28 grayscale images as input. A 2x2 max pooling layer then reduces the spatial size of the feature maps, and the result is flattened into a one-dimensional vector. This is followed by a dense layer with 32 units and ReLU activation to learn more complex patterns. The network ends with a dense layer of 10 units with softmax activation, producing a probability distribution over the 10-digit classes from 0 to 9. The model is compiled with key training settings. It uses the Atom optimizer, which is efficient and adapts well during neural network training. The loss function is sparse categorical cross-entropy, appropriate for multi-class classification when labels are given as integers. The model also tracks accuracy as a metric, so we can monitor how often it correctly predicts the target classes during training and evaluation. We first set up a base directory named for TensorBoard logs, which will hold all the training log files. To make sure this directory exists, we call a function that creates it if it is not already present. This step prepares the logging infrastructure so TensorBoard can properly store and access training information. To create a unique directory for TensorBoard logs, we generate a run identifier based on the current date and time, including details like year, month, day, hour, minute, and second. This timestamp string makes each training run distinct. We then join this identifier with a base log directory to form the full path for storing logs. This approach keeps logs from different training sessions organized and makes it easier to track and compare results. We set up a TensorBoard callback to track training metrics using the chosen log directory. The histogram logging is turned off, so it does not record weight histograms. The option to write the computational graph is enabled, allowing us to visualize the model structure. Image logging of model weights is disabled to avoid storing unnecessary data. This configuration lets us monitor training in TensorBoard while keeping the logs lightweight. We use an early stopping callback in Keras to monitor validation loss during training. If the validation loss does not improve for 2 training epochs in a row, the process stops early instead of continuing unnecessarily. The callback also restores the model weights to the best version seen during training, helping ensure the final model has optimal performance. We first define where to save the best model by combining the main logging directory with a file name for the model. Then we create a Keras model checkpoint callback that watches the validation loss during training. Whenever the validation loss reaches a new minimum, the callback saves the model's weights to that location. This way, only the best performing version of the model is stored for later evaluation or deployment. We train the model using the fit method, providing the training data and labels, and reserving 20% of this data for validation to track performance on unseen examples. Training runs for up to 5 epochs with batches of 64 samples, but it can stop early if the validation loss stops improving. We use 3 callbacks, one to log information for TensorBoard, one for early stopping, and one to save the best version of the model based on validation loss. The training output is kept quiet by setting the verbosity level to 0. To check how well the model performs on unseen data, it is evaluated on the test set using the model's evaluation function with the test features and labels. The evaluation runs silently, without showing progress messages. This process returns 2 key results: the loss, which measures how far the predictions are from the true values, and the accuracy, which shows the proportion of correct predictions. These values are stored for later inspection and analysis of the model's performance on the test data. The code prints a message that tells you where the TensorBoard logs are stored. This helps you later track and visualize how training progressed. It uses a variable that holds the directory path, so you know the exact location of these logs. The code prints the location where the best model checkpoint is saved. This tells you exactly where to find the version of the model that achieved the lowest validation loss during training. The checkpoint path was set up earlier in the script so that this top-performing model is easy to locate and reuse for later evaluation or deployment. At the end, the script reports the model's final performance on the test data by printing the test loss and test accuracy, rounded to 4 decimal places. These values give a compact summary of how well the trained model handles data it has not seen before. Together, they provide a quick indication of the model's ability to generalize beyond the training set. This script builds and trains a simple convolutional neural network in TensorFlow and Keras to classify images from the MNIST dataset. It checks for a GPU and uses it if available, loads a reduced subset of the data for faster training, and normalizes and reshapes the images for the model. The network uses a basic stack of convolution, pooling, and dense layers, and is trained with the Atom optimizer and sparse categorical cross-entropy loss. During training, it uses TensorBoard logging, early stopping to reduce overfitting, and model checkpointing to save the best version. After training, it evaluates the model on a test set and reports the final loss, accuracy, and where the logs and best model are stored. Monitoring training curves. Inspecting history objects. After training a model, the history object is the main tool for understanding how it learned. It records how metrics such as loss and accuracy change over each epoch, including validation metrics if they were used. This gives you a timeline of performance on both training data and unseen data. Reviewing this learning progress provides a deeper understanding of model behavior than looking only at the final loss or accuracy values. The history object records how metrics like loss and accuracy change over training epochs, usually including matching values for validation data. Each metric is stored as a sequence of values, so you can see trends over time. By comparing training and validation metrics, you can tell whether the model is improving, leveling off, or getting worse. For example, if training accuracy keeps rising, but validation accuracy stops improving, that suggests overfitting and weaker generalization beyond the training data. When reviewing the training history of a model, focus on how metrics change over time rather than on single values. If both training and validation losses remain high, the model may not be suitable for the task and could be underfitting. If validation loss starts to rise after initially improving, this suggests overfitting. By recognizing these patterns, you can judge when learning is effective and decide whether to visualize data, change training duration, or apply regularization. Python code, inspecting history objects. This script demonstrates how to examine history objects from model training, with a focus on how training and validation metrics change over time. By looking at these metric curves, you can see patterns that indicate whether a model is underfitting or overfitting. Use it to connect the shape of these trajectories with the model's generalization performance. The line with the exclamation mark is a command to install TensorFlow version 2.20.0. Using this exact version, make sure the script runs with the library it was designed for. This helps prevent compatibility problems that could occur with newer or older versions. Specifying library versions like this is a common way to keep machine learning projects consistent across different environments. This code begins by importing three key libraries. It brings in the operating system library to work with files and environment settings, the random library to generate random numbers and make random choices, and NumPy for efficient numerical computing. NumPy is especially important for handling arrays and performing fast mathematical operations. Together, these imports prepare the program to manage the system, use randomness, and carry out complex calculations. We start by importing TensorFlow, a library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. We then import the layers tools from Keras, which provide components like convolutional and dense layers. Together, these imports give us the essential tools to define and train deep learning models efficiently. This line checks and prints the version of TensorFlow currently in use. It helps you confirm that your environment is set up correctly and matches the version your code expects. Knowing the exact version is important for debugging and for understanding any behavior or features that depend on a specific TensorFlow release. We set a seed value, such as 42, to make our results reproducible. By fixing the seed for the random module, we ensure that any random numbers it generates are the same each time the program runs. We then do the same for NumPy's random number generator so that all NumPy operations involving randomness are consistent. Finally, we set the seed for TensorFlow's random number generator so that operations like weight initialization behave deterministically. This consistent behavior across runs is essential for debugging and verifying results. We begin by loading the MNIST dataset using the dataset tools in Keras. MNIST is a standard collection of handwritten digit images used to train and test image processing models. The data is divided into training images and labels, and separate testing images and labels. This split lets us train the model on one portion of the data and then evaluate its performance on different unseen examples. Using this approach helps us check whether the model generalizes well beyond the data it was trained on. To keep the runtime low, the code uses only a smaller subset of the available data. It limits the training set to 4,000 samples and the test set to 1,000 samples, then slices the data so only those first samples are used. By reducing the number of training and test examples, the model can be trained and evaluated more quickly, while still demonstrating the overall process. To speed up model evaluation, the test set is reduced to only the first 1,000 samples. This is done by slicing the arrays that store the test images and their labels. Using a smaller subset makes the evaluation process faster and more efficient, while still providing a quick check of the model's performance. The code prepares the image data by converting the pixel values in both the training and test sets to a float32 format, which is suitable for numerical work in machine learning. It then normalizes these pixels by dividing each value by 255, changing their range from 0 to 255 into a range from 0 to 1. This normalization step helps the neural network train more effectively and remain more stable during learning. To prepare image data for convolutional layers, we need to add a channel dimension to both the training and test sets. We do this by expanding the shape of the data arrays so that a new dimension is added at the end. This format is standard for image inputs, where each pixel is treated as having a single channel, such as in grayscale images. Adding this channel dimension ensures the data matches the input format expected by convolutional layers. Before building the neural network, the code first prints the shapes of the training and test datasets. This step checks that the data and labels for both sets have the correct dimensions. By confirming that these shapes match the model's expected input format, it helps ensure the data is properly prepared and ready to be used for training and evaluation. We build a small convolutional neural network using a sequential model that takes 28 by 28 grayscale images as input. It begins with a two-dimensional convolutional layer with 16 3x3 filters and a ReLU activation, followed by a 2x2 max pooling layer to reduce the spatial size of the feature maps. The output is then flattened into a one-dimensional vector and passed to a dense layer with 32 units and ReLU activation to learn more complex patterns. Finally, a dense output layer with 10 units and a softmax activation produces class probabilities for the 10-digit categories in the MNIST dataset. We begin by compiling the model, which means defining how it will be trained. We choose the Atom optimizer because it is efficient and adapts well during neural network training. For the loss function, we use sparse categorical cross-entropy, which is appropriate for multi-class classification when the labels are given as integers. We also track accuracy as the main metric, so we can monitor how well the model is learning to classify the data correctly during training. The model is trained using a fit function that takes the training data and labels and runs for 8 epochs, meaning it goes through the entire dataset 8 times. It uses a batch size of 64, so it updates its weights after processing 64 samples at a time. During training, 20% of the data is held out as validation data to monitor performance on unseen examples. The training runs without printing progress to the console, and the fit function returns a history object that records metrics such as loss and accuracy for each epoch. The history dictionary from the history object stores how metrics such as accuracy and loss change at each training epoch. By reading these recorded values, we can track how the model's performance evolves over time. This information helps us understand the training process and identify problems such as overfitting or underfitting. In short, analyzing the history dictionary is key to diagnosing and improving model training behavior. The code displays the keys stored in the history dictionary, which represent the names of the metrics tracked during training. These keys indicate what information is available for each epoch, such as accuracy and loss, for both the training and validation data. By listing these metric names, you can quickly see what performance data was recorded and then use it to access and analyze how the model behaved over the course of training. We obtain the training accuracy values from the history dictionary using the accuracy key, which gives us a sequence of accuracy measurements for each training epoch. In the same way, we extract the validation accuracy values using the validation accuracy key, producing a sequence of accuracy scores on the validation set for each epoch. By comparing these two sequences over time, we can see how the model's performance evolves on both the training data and the validation data during training. We start by retrieving the training loss values from the history data, which gives us the loss recorded at each epoch during training. We also extract the validation loss values in the same way. Together, these two sequences let us compare how the model performs on the training data versus the unseen validation data over time. This comparison helps us understand how the model is learning and whether its performance generalizes beyond the training set. We examine the model's training progress over the first 3 epochs by looking at accuracy and loss for both training and validation. For each epoch, we take the accuracy and loss values from their lists, convert them to floating point numbers for precision, and then format them consistently. We print the epoch number along with training accuracy, validation accuracy, training loss, and validation loss, each rounded to 3 decimal places. This gives a clear, concise snapshot of how the model's performance changes during the initial stages of training. The code first finds the index of the final training epoch by taking the length of the training accuracy list and subtracting 1, which points to the last recorded metrics. It then prints the epoch number along with the training accuracy and validation accuracy for that final epoch. These values are formatted to 3 decimal places for readability. This output lets you quickly compare the model's performance on the training and validation data at the end of training and see how well it has progressed overall. We use the plotting tools from the matplotlib library, specifically the pyplot interface, to create visualizations like graphs and plots. These visualizations help us see data trends and patterns more clearly. In this script, we use them to plot training and validation loss across epochs, so we can track and better understand how the model's performance changes over time. We create a compact plotting window and draw 2 lines showing how training loss and validation loss change over the epochs. The training loss line represents performance on the training data, while the validation loss line shows performance on separate validation data. We label the horizontal axis as epoch and the vertical axis as loss, and give the plot a title describing it as the training versus validation loss trajectory. A legend is added so we can easily distinguish the 2 lines. The layout is adjusted so labels and titles fit clearly, and then the plot is displayed for visual inspection of the loss trends during training. This script shows how to inspect the training history of a neural network in TensorFlow and Keras. It builds a small convolutional model on a subset of the MNIST dataset and trains it for 8 epochs, storing the results in a history object. From this history, it extracts and prints the training and validation accuracy and loss for the first few epochs and the final epoch, to reveal how these metrics change over time and to spot underfitting or overfitting. It then uses a plotting library to draw training and validation loss curves, giving a clear visual summary of how well the model learns and generalizes to unseen data across epochs. Visualizing training metrics. Visualizing training metrics turns raw numbers into a clear picture of how a model is learning over time. By plotting loss and accuracy across training epochs for both the training and validation sets, you can see whether performance is improving, leveling off, or diverging. This helps you judge if the model is truly learning patterns that generalize to new data or simply memorizing the training set. For example, a smooth decline in both training and validation loss suggests the model is capturing meaningful features rather than noise. When visualizing training metrics, focus on key curves such as loss and accuracy for classification tasks, or loss and error measures for regression. Plot both training and validation metrics on the same graph so you can easily compare how they change over time. For example, in a sentiment analysis model, you might see training accuracy keep rising while validation accuracy levels off, which is much clearer on a graph than in raw logs. Similarly, in a house price prediction model, plotting errors across epochs helps you see whether continued training is actually reducing generalization error or simply causing overfitting to the training data. Visualizing training metrics helps you see how changes like learning rate, batch size, or model architecture affect learning progress. By comparing different training runs, you can observe how these choices shape the loss curves and improvement patterns. For instance, a learning rate that is too high may cause unstable loss, while a more moderate rate produces smoother declines. An increasing model capacity may reduce training loss but raise validation loss, indicating overfitting. These visualizations serve as a diagnostic tool, making the training process more transparent and enabling systematic refinement of your models. Python code. Visualizing training metrics. This script is designed to visualize training and validation metrics while a model learns. It works on a very small subset of the MNIST dataset so that everything runs quickly, The main goal is not high accuracy, but to help you practice reading and interpreting training curves. The line starting with an exclamation mark is a shell command that installs TensorFlow version 2.20.0. Using this exact version helps ensure the script is compatible with the rest of the code. The exclamation mark shows that the command is meant to be run in a Jupyter notebook or a similar environment that can execute shell commands directly. We start by importing 3 key libraries. The operating system library lets us interact with the system for tasks like working with files and environment settings. The random library is used to generate random numbers, which is important for things like shuffling data or setting random seeds. Finally, the numerical computing library NumPy provides efficient tools for working with arrays and performing fast mathematical operations. We begin by importing TensorFlow, a library used to build and train machine learning models. Within TensorFlow, we use Keras, a high-level interface that makes it easier to create neural networks. We also import the layers module from Keras, which provides components such as convolutional and dense layers. Together, these imports give us the essential tools to define and train our neural network efficiently. To make code produce the same results every time it runs, we set a fixed seed value, such as 42, for all random number generators. We first set the seed for Python's built-in random functions, then for the random functions in the NumPy library, and finally for TensorFlow's random operations. This controls how random numbers are created in each library, including things like neural network weight initialization. Using this deterministic setup is important for reliable debugging and for fairly comparing results across different runs. This line displays the version of TensorFlow that is currently in use. Knowing the exact version helps you check compatibility with other tools and libraries. It is also useful for debugging, because different TensorFlow versions can have different features or behaviors. By printing the version, you can quickly confirm that your environment matches what your code expects. The code first checks whether any GPUs are available by asking TensorFlow for a list of physical GPU devices. It then converts this list into a simple true or false value that indicates if at least one GPU is present. Finally, it prints a message stating whether a GPU is being used, giving you quick feedback about the hardware setup for training. We begin by loading the MNIST dataset using the dataset tools provided by Keras. This loading step returns 2 sets of data, one for training and one for testing, and each set includes both images and their labels. MNIST is a standard collection of handwritten digit images used to train and evaluate image processing models. By loading it in this way, we can conveniently access the images and their correct digit labels for both training and evaluation. To make the demonstration run faster, the code works with a smaller dataset. It limits the training set to 4,000 samples and the test set to 1,000 samples. The training data and labels are both sliced so that only the first 4,000 entries are used. This reduction speeds up processing and makes it easier to quickly visualize and interpret the results. To speed up this demonstration, we reduce the size of the test dataset by using only a smaller subset of the test images and their labels. Specifically, we select just the first part of the test data, up to the number defined as the desired test sample size. Working with fewer test samples makes the process faster, while still allowing us to illustrate how the method works. To prepare the images for a neural network, the training data is first converted to floating point numbers, and then each pixel value is divided by 255. This rescales all pixel values to fall between 0 and 1, which is a standard normalization step. The same conversion and scaling are applied to the test images so that both training and testing data are processed in a consistent way. To prepare image data for convolutional layers, we need to add a channel dimension to both the training and test sets. We do this by expanding the data along the last axis, which adds a new dimension of size 1. This converts each image from a 2-dimensional array into a 3-dimensional array, where the third dimension represents a single color channel. Applying the same transformation to both datasets ensures they share the same shape, which is required for the convolutional neural network to process the images correctly. We begin by printing the shape of the training data, which includes both the images and their labels, to confirm that everything has been loaded and pre-processed correctly. We then do the same for the test data, checking the shapes of its images and labels as well. These simple checks verify that both datasets have the expected dimensions and are properly aligned. Confirming this before building the neural network is essential, because the model relies on the input data matching the required format. We build a small convolutional neural network using a simple stack of layers. It starts with a 2-dimensional convolutional layer with 16 3x3 filters and ReLU activation, taking 28 by 28 grayscale images as input. A 2x2 max pooling layer then reduces the spatial size of the feature maps. The result is flattened into a 1-dimensional vector and passed to a dense layer with 32 units and ReLU activation to learn more complex patterns. Finally, an output dense layer with 10 units and softmax activation produces class probabilities for the 10 MNIST digit categories. We begin by compiling the model, which means defining how it will be trained. We choose the Atom optimizer because it is efficient and adapts well during neural network training. For the loss function, we use sparse categorical cross-entropy, which is appropriate when class labels are given as integers in a classification task. We also track accuracy as the main metric, so we can monitor how well the model is learning to correctly classify the data during training. We train the model using the Keras fit method, which takes the training data and labels and runs for 8 epochs, meaning it passes over the entire dataset 8 times. The batch size is set to 64, so the model updates its weights after every 64 samples. We also reserve 20% of the training data for validation, allowing the model's performance to be evaluated after each epoch. Training logs are turned off by setting the verbosity to 0, and the fit method returns a history object that records metrics such as loss and accuracy over the epochs. The code retrieves the training history produced during model fitting, which stores metrics for each epoch, such as loss and accuracy. These recorded values show how the model's performance changes over time. By extracting this history, we can later plot and analyze these metrics to see how well the model is learning and generalizing. We use the PyPlot module from the matplotlib library to create visual plots of our data. This tool is important for generating graphs and other visualizations. It allows us to easily display training and validation metrics, so we can analyze how well a model is performing. We begin by creating a new plotting window using the figure function from the matplotlib library. This sets up a blank canvas where we can draw our graph. We choose a size of 6 by 4 inches so the plot is clear and easy to read. This figure will be used to display the training and validation loss values across the different epochs. We examine how the model learns by plotting the training loss over the epochs, which shows how its error on the training data decreases. We then plot the validation loss over the same epochs to see how well the model performs on unseen data. By comparing these two labeled curves, we can visually assess both learning progress and generalization during training. We create a plot where the horizontal axis shows the epoch number, meaning how many full passes we have made through the training data, and the vertical axis shows the loss, which measures the error between predictions and actual values. We give the plot the title, Training versus Validation Loss, to clearly state what is being compared. Finally, we add a legend so listeners can distinguish between the training loss curve and the validation loss curve, making the graph easier to understand and interpret. We then display the plot using the plotting library's show function, which reveals the training and validation loss curves over the epochs. Viewing these curves helps us see how well the model is learning over time. By examining their shapes and how they diverge or align, we can detect problems such as overfitting or underfitting. This insight guides us in deciding how to adjust the model or training process. This script trains a small convolutional neural network on a reduced version of the MNIST handwritten digit dataset. It sets a random seed for reproducibility, checks for GPU support, loads and normalizes the data, and then defines a simple model with convolutional and dense layers. The network is compiled with the Atom optimizer and sparse categorical cross-entropy loss, and trained for 8 epochs, with a part of the data held out for validation, while suppressing detailed training output. After training, it uses a plotting library to show how the training and validation loss change over epochs, so you can visually evaluate the model's learning progress and potential overfitting. Spotting overfitting trends. When you monitor training curves, you can spot overfitting by comparing training and validation performance. Overfitting happens when a model memorizes details of the training data instead of learning patterns that generalize. In this case, training loss keeps decreasing and training accuracy may become very high, but validation loss stops improving and starts to rise, while validation accuracy levels off or drops. This growing gap between training and validation results shows the model is getting better on the data it has seen, but worse on new data, such as a churn model that performs much better on its training set than on its validation set. When monitoring model training, you need to distinguish normal noise in validation metrics from true overfitting. Early in training, especially with small datasets, validation loss and accuracy can jump around, so brief spikes or dips are not a concern. Overfitting becomes clear when over several epochs, training loss keeps going down, while validation loss rises and validation accuracy stops improving. In tasks like image classification, this often means the model is starting to memorize noise or irrelevant details instead of learning patterns that generalize. Recognizing this turning point tells you it is time to adjust your training strategy. Recognizing overfitting in your training curves is essential for making good training decisions. When training performance keeps improving, but validation performance stalls or drops, it means the model is learning patterns that do not generalize to real data. In this situation, continuing to train can actually harm real-world performance. By spotting this early, you can stop training at a better point or adjust your approach with techniques like regularization, better data, or a simpler model. Building this intuition helps you avoid wasting resources and ensures the model works well on the data that truly matters. Python code, spotting overfitting trends. This script demonstrates overfitting by examining training curves for a small model trained on MNIST digit data. It fits the model on the training set and tracks how the loss changes over time. At the same time, it measures loss on a separate validation set. Finally, it plots both training and validation loss trends so you can see when the model starts to memorize the training data instead of generalizing well. The commented line recommends installing TensorFlow version 2.20.0 to match the code's requirements. This is a reminder that different TensorFlow versions can behave differently. By fixing the version, the code reduces the risk of errors or unexpected behavior that might occur if a different version of the library is used. We begin by importing several key libraries needed for our work. The operating system library lets us interact with the system environment, and the random library allows us to generate random numbers, such as for shuffling data. We then import NumPy for efficient numerical computations and array handling. Finally, we bring in TensorFlow, which we will use to build and train a machine learning model on the MNIST dataset. We set a seed value, such as 42, so that all random operations become reproducible and give the same results each time we run the code. This seed is applied to Python's random module, to the random number generator in NumPy, and to TensorFlow's random number generator. Doing this is especially important in deep learning, where random weight initialization and other stochastic processes can otherwise change from run to run. By setting these seeds, we create a controlled environment where experiments can be repeated reliably and results can be compared fairly. This line of code displays the version of TensorFlow that is currently in use. It provides a quick check that the correct version of the library is installed. Confirming the version helps ensure compatibility and that the rest of the code will run as expected. The code first checks whether any physical GPUs are available using TensorFlow's configuration tools. If it finds at least one GPU, it selects the GPU as the device so computations can run faster. If no GPU is detected, it falls back to using the CPU, which is typically slower for deep learning tasks. It then prints which device type was chosen, indicating whether the model will run on a GPU or on a CPU. We begin by loading the MNIST dataset using the dataset loading tools in TensorFlow's Keras library. This call returns two sets of data, one with training images and their labels, and another with test images and their labels. MNIST is a standard dataset of handwritten digit images that is widely used to train and evaluate image processing models. It is especially useful here because it provides a clear way to demonstrate how a model can overfit to the training data. The code first prints the shapes of the training and test datasets for the MNIST data. This confirms that the data has been loaded correctly and that the number of samples and features matches what we expect. By checking these dimensions before any subsampling or preprocessing, we ensure that all later operations are applied to data with the correct structure. To speed up training and make experiments more manageable, we work with a smaller version of the MNIST dataset. We set the training set size to 4,000 samples and the validation set size to 2,000 samples. From the original MNIST training data, we simply take the first 4,000 images and their corresponding labels as our reduced training set. This smaller dataset allows quicker experimentation and makes it easier to observe overfitting behavior. To create a validation set from the MNIST training data, we take a slice of the training images and use it as a separate subset. We choose a block of images starting at a specific index and include as many as we need for validation. We then take the matching labels from the training labels, so each validation image has the correct label. This split gives us a properly labeled validation set that lets us evaluate the model on data it does not directly train on. The code preprocesses the training and validation images by converting their pixel values to floating point numbers and scaling them to range between 0 and 1. It does this by dividing each original pixel value by 255. Normalizing the data in this way is a standard step for image inputs and helps the neural network train more effectively and with greater stability. To prepare our grayscale image data for convolutional layers, we need to add a channel dimension to both the training and validation sets. We do this by using a function that expands the array dimensions along the last axis, creating a new dimension that represents the single color channel. Applying this step to both datasets ensures they have the correct shape required as input for the convolutional neural network. After pre-processing the data, we check the shape of the training dataset to confirm its dimensions. This step ensures the data has been correctly resized and reshaped for the model. We do the same for the validation dataset, verifying that its dimensions are also correct. These simple checks are essential to make sure both datasets are in the expected format before starting model training. We build a small convolutional neural network with Keras to recognize handwritten digits from the MNIST dataset. It starts with a two-dimensional convolutional layer with 16 3x3 filters and ReLU activation, taking 28 by 28 grayscale images as input, followed by a 2x2 max pooling layer to downsample the feature maps. The pooled features are then flattened and passed to a dense layer with 64 units and ReLU activation to learn more complex patterns. A final dense layer with 10 units and softmax activation outputs class probabilities for the 10 possible digits. This simple architecture is effective for digit recognition and small enough to clearly show overfitting behavior. The model is now being compiled, which prepares it for training. An atom optimizer with a small learning rate is chosen to update the model's weights and reduce the loss. The loss function is sparse categorical cross-entropy, which is appropriate for multi-class classification with integer labels. Accuracy is also tracked as a metric, so we can monitor how well the model performs during training and validation. Together, these choices ensure the model is properly set up to learn from the data. The model is trained using a fit procedure that takes the small training dataset and its labels and runs for 40 epochs to deliberately encourage overfitting. It uses a batch size of 64, so the weights are updated after every 64 samples. Validation data is included to track how well the model performs on unseen examples during training. The training runs silently with no progress output. This setup is designed to show how the model's performance evolves over time, with a particular emphasis on observing overfitting. We use the model's training history to extract two key measures: training loss and validation loss. The training loss shows how well the model fits the training data over each epoch, while the validation loss shows how well it generalizes to new, unseen data. By examining these two loss curves together, we can identify patterns such as overfitting, where performance on the training data improves, but performance on the validation data gets worse. The code reports the final training loss by taking the last recorded value, rounding it, and printing it to show how well the model fit the training data. It then does the same for the final validation loss, which reflects performance on unseen data. Comparing these two values helps you judge whether the model is overfitting, since a much lower training loss than validation loss suggests the model does not generalize well. The code compares the validation loss at the final epoch with the lowest validation loss seen during training to check for overfitting. If the final validation loss is higher than this minimum, it reports that validation loss increased after reaching its lowest point, which suggests overfitting. If the final validation loss is not clearly higher, it reports that there is no clear increase, implying that overfitting may not be a serious issue. We use the pyplot module from the matplotlib library, which is a common tool in Python for creating visualizations. In this context, it will be used to plot the training and validation loss over time. These plots help us visually examine how the model is learning and make it easier to spot issues such as overfitting. We begin by creating a plotting area for the loss curves using a figure from a plotting library. The figure size is set to 6 by 4 inches, so the resulting plot is clear and easy to read. This size offers a good balance between showing enough detail in the curves and keeping the overall view understandable when displayed. We use a plotting library to show how the training loss changes over the epochs. This graph reveals how the model's error on the training data decreases as it learns. By examining this curve, we can better understand the learning process and spot signs that the model might be overfitting. We now plot the validation loss across training epochs using a line graph. This graph shows how the validation loss values change as the model trains, and we label the line as validation loss so it can be distinguished from other lines in the legend. By examining this plot, we can see trends in the model's performance on validation data and gain insight into issues such as overfitting. We create a plot where the horizontal axis shows the epoch, or how many training cycles have been completed, and the vertical axis shows the loss, which measures the error between predicted and actual values. The title explains that the graph compares training loss and validation loss over these epochs. A legend is included so listeners can clearly distinguish the line for training loss from the line for validation loss, making the plot easier to interpret. The plot is finally displayed using the show function from the plotting library, so we can see how the training and validation loss change over the epochs. By examining these loss curves, we can visually assess the model's performance. This helps us detect patterns such as overfitting, where the training loss keeps improving, but the validation loss stops improving or gets worse. This script demonstrates overfitting by training a small convolutional neural network on a reduced version of the MNIST dataset. After setting up reproducible conditions and preparing the normalized image data, it builds and trains a simple model for many epochs while tracking training and validation loss. Once training is complete, it checks whether the validation loss starts to rise after reaching its lowest point, while the training loss keeps decreasing. This divergence between training and validation loss is the classic pattern that indicates the model is overfitting to the training data. In this lecture, you learned to configure model.fit with appropriate batch sizes, epochs, and validation strategies for a given dataset. Use Keras callbacks to monitor training, implement early stopping, and save model checkpoints. And interpret training and validation curves to diagnose underfitting and overfitting. In the next lecture, Lecture B, we'll go over custom training loops.
Thank you for your attention. See you all in the next lecture.